So, any questions? Yeah.
Could you take from the guide the 3C2?
So can you tell me the question, because I don't actually have a printout of the handouts in front of me.
You're given two sorted arrays.
Mm-hmm.
One has m elements, the other has n.
Okay.
And then it's an integer k.
And you want to find the kth smallest element in the union?
Yeah.
Is that right? Okay. All right. So there's a part A to this question, which is let's assume that m, n, and k are all equal. Okay, just partly to build up some intuition, but partly because, in fact, this is the only interesting case, which we'll see in a minute. All right, so the idea is now I'm given these two arrays, A and B, and I want to find the median element in their union. This doesn't sound like a graph problem. This doesn't sound like a dynamic programming problem. We saw medians of other things in the context of divide and conquer. Probably this is some sort of divide and conquer recursion problem. Now I know I could just glue the two arrays together and find the median in linear time. Or I could merge the two arrays together into a single sorted array in linear time and then find the median in constant time. So let's try to do better than that. And so I want to try to get rid of some constant fraction of the input using only a small amount of work. So what I'm going to try to do is compare the two elements, little a and little b, that are right in the middle of these two arrays. And there are two possibilities for what can happen, but I'll show you one of them. Suppose the median of array A is smaller than the median of array B. Then I know that everything I know everything in the left half of A is smaller than A. I also know that everything in the left half array is smaller than B. Similarly, I know that everything in the right half of the array is larger than A and larger than B in the other array. Okay. I also know that B is bigger if I let this is n over 2, or sorry, n over 2. B is larger than n things in the union. Specifically, B is larger than these n over 2 things on the left side of B. B is larger than these n over 2 things on the left side of A. And B is actually larger than A. Okay? So B is bigger than half of the elements of this array. Right? Symmetrically, I know that A is smaller than half of the elements of the array. So anything bigger than B is useless. Anything bigger than B is way too big to be the median. And symmetrically, anything smaller than A is way too big to be the median. Okay? So I can just throw out the bottom half of A and the top half of B, and now I'm left with 2 arrays, each of size n over 2. And notice that I threw out n over 2 things. I used to be looking for the nth largest, or sorry, the nth smallest. Now I'm looking for the item of rank n over 2 and what's left. In other words, now I recursively find the item with rank n over 2 in the arrays from A, n over 2 to n, and B from 1 up to n over 2. Right? And this is the same problem that I started with, but just with the size of the arrays divided by 2. Yes?
How does this change if you have even-sized arrays? Because they're not...
If I have even-sized arrays, I throw some infinities onto the ends, and I don't worry about it. Right? On an exam, on floors and ceilings and things like that, I'm just going to say, okay, fine. Glue an infinity on one end of A and a minus infinity on one end of B, and be done. Okay. So I end up with an algorithm that to find the median of the union of 2 sorted arrays of size n, I do a constant amount of work, and then I recurse on an array of size n over 2. This is, of course, the recursion for binary search, and so I end up with log n time. Okay. The case where little b is smaller is exactly symmetric. I end up throwing out the other halves of A and B. Okay? But the basic argument for how I decide to throw things away is to say, by doing this comparison, I can identify a certain chunk of the input that I know absolutely for sure is smaller than the median. And I can identify another chunk that I know absolutely for sure is larger than the median. So I'm going to try the same strategy in the general case. So I've got an array A, and I've got an array B. And I'm looking for the kth smallest element for some k. Let me first think about what happens when k is reasonably small. Okay. Let's suppose the size of A is 20 and the size of B is 100 and k is 10. Without doing any comparisons at all, I can already throw out most of the input. Okay? In particular, I know that the 10th smallest element in this union can't be in the top half of A because everything here is bigger than 10 things, namely the bottom half of A. Similarly, I can throw out anything past B sub 10 because all of these elements are bigger than more than 10 things in B. Right? So in this case, I've now reduced immediately to 2 arrays of size 10, and I want to find the 10th smallest thing. And so I'm back to part A. All right. Now there's a symmetric case. Let's say A has size 20 and B has size 100 and K is 90. Okay. I can, in other words, I'm looking for the 30th largest thing. I can already throw out, I can keep these 30 things, but I can already throw out most of B. Now, I'm going to throw out 70 things here, which means when I recurse, I'm actually looking for 20 things. The 20th largest thing, and now it looks more like I'm in the first case again. So it takes, there are several cases to consider here, but the basic observation is by comparing n, m, and k, I can actually identify an interval of length k in A and an interval of length k in B that must contain the target element I'm looking for. And then I'm just going to call part A. Yes?
You're looking for the 90th largest element. Why did you only...
I'm looking for the 90th. Well, so what this means is I'm looking for something that I know has only 30 things larger than it. The reason I can throw out this stuff is because I know everything in this left range has too many things that are bigger. Right? That's my criterion for cutting it off. No, I want the 90th biggest element of the union. There are 120 elements altogether. Right? Right. On the other hand, I guess this is where I actually do the recursion. I can throw out the 10 largest elements of B because each of these is bigger than more than 90 things. And so again, I'm left with two windows of size 20. And I'm looking for the 20th largest thing in those arrays. Okay, so actually working out the thing in complete detail requires some case analysis, but ultimately you end up just reducing back to part A. Now there's another way that you can do this, which is to say the following. So I'm going to imagine lining up A and B, and I compare the middle element of A and the middle element of B, just like I did in the first algorithm. And now I know if I do this comparison, and say little a is smaller, that the bottom half of A must be smaller than the median and the top half of B must be larger than the median. So if the thing that I'm looking for is larger than the median, I can throw out the bottom half of A. If the thing I'm looking for is bigger than the median, I can throw out, if the thing I'm looking for is bigger than the median, then it must be bigger than everything in this left half of A, so I can throw out the left half of A. If the thing I'm looking for is smaller than the median, then it must be smaller than everything in the right half of B, so I can throw out the right half of B. If I actually am looking for exactly the median, I can throw out both of these subarrays. Okay. And then now the observation is in one step, I have cut one of the two arrays in half, at least. Maybe both, but at least one of them. Yes?
If you're looking for median, and you throw out both.
What do you mean, how do I know which one? The left half of A is too small and the right half of B is too big, so I can throw those away. And when I recurse, I threw out fewer things below the target element and more things above, so I'm no longer looking for the median, I'm looking for something else.
And that's for the problem when you actually are trying to find the median?
Huh?
It's going to be either A or B, right?
No. 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 The median of A is little a, and the median of B is little b. The median of A union B might be over here, because all of these things are actually quite small. So in any case, with one comparison, you either split, you either have, cut A in half, or you cut B in half, or possibly both. And so I can only cut A in half log n times, and I can only cut B in half log m times before I'm down to two constant size arrays, at which point I just use brute force. Okay, so this algorithm actually also ends up giving you a running time of log n plus log m, just because log n is the number of times I can cut A in half, and log m is the number of times I can cut B in half. Yes?
In this case, I want to compute the median.
In this case, you want to solve the problem at the top of the screen. I'm given two arrays, not necessarily the same size, and I'm given an integer k, which is not necessarily n plus n over 2. Right? I do this comparison between the middle element of A and the middle element of B, and then depending on how big k is, I either throw out half of A or I throw out half of B, or if I'm really lucky, I can actually throw out both. Right? But no matter, no matter what K is, I can always identify at least half of one of those two arrays that I can throw out. And then I recurse on what's left.
So depending on your K.
Yeah, depending on your K. So if K is bigger than n plus m over 2, then I'll throw out the bottom half of A here. If K is less than n plus m over 2, I'll throw out the top half of B. So there's like 4 different cases depending on how K relates to n and m and how the middle of A relates to the middle of B. So there's a bunch of if, then, else. But the cases end up all looking really symmetric in the end.
The next time when you do the
Yes, whenever I throw out elements that are smaller than K, I decrease K by that number. Just like when we did selection in regular selection in class. Right. So either of these 2 approaches to part B will work. One, you can just do some pre-processing and realize you're solving part A. Or you can solve it using a modification of the algorithm used to solve part A. Given the choice, I recommend doing this, just because it ends up being fewer cases. Yes? Yep.
Do we know how to find the smallest element in the class?
Okay. So you have a bitonic array, and I want to find the smallest element. So just so everyone is on the same page, what bitonic means is that I have one local minimum and one local maximum, even if I can wrap around. All right, so here, 3, 4, 6, 9, 8. So here's my local maximum. 7, 5, 1, 2. Here's my local minimum. Okay, so there's exactly one element that is bigger than both of its neighbors, even if that element might be the last element in the array. Right, so this array is actually bitonic. 3, 4, 6, 9. 9 is bigger than 6, and it's bigger than 3. Right, so really just think of this as a circle. And there's one local minimum, and the local minimum is the one that you're trying to find. Okay. Does the problem actually state a time bound? Log n. Right, so you want to do some kind of binary search. And so what this suggests is that I want to do a small amount of work and somehow be able to recurse on half of the array. Right? Now, one thing to notice is that when I pick half of the array, whichever half I pick, that half of the array will be bitonic. A subarray of a bitonic array is still a bitonic array. Okay, so when I recurse, I really can just recurse. So the trick is going to be somehow, how do I figure out whether the minimum is going to be on the left or going to be on the right? And so the picture that I would want you to have in your head, the array looks something like this, where I suppose to be mnemonic, I should put the blue portal on this side and the orange portal on that side. Okay, so there's this thing that wraps around, it goes up, and then it goes down, and then it wraps around. But the portals could be anywhere inside this up-down sequence. That's the whole point, is I don't know where in the up-down sequence the portals are. Yes? Yes, so if I start at the max and I go to the min, I have to go down, 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 because if I ever go up and then down again, that would give me another local max. Okay? So for example, if I swapped 7 and 5, I would no longer have a bitonic array, because then the 7 would be bigger than 2 of its neighbors, right? And so would the 9. Okay? So I want to do some local tests to get some information about the array. So one thing that I can ask is, first of all, I've got this weird circular stuff going on. It'd be nice to kind of break that. So the first thing I'm going to do is I'm going to compare the elements at the ends of the array. And in this case, I'll notice that the last element of the array is smaller than the first, right? Which means that the shape of the array is going to look something like what I've drawn in this picture, as opposed to looking like, the reflection, right? So this is just to remove a source of symmetry, right? I'm going to say, compare 1 and n, and now, without loss of generality, assume that a1 is bigger than an, because the other case will be symmetric. You'll just have a copy of the code, and you'll change some signs. And now, if I'm trying to do some sort of binary search-like thing, I want to do something near the middle of the array that will give me some information. So, can anybody suggest a question that I could ask about some stuff in the middle of this array that would reveal something? Yeah.
Since you get constant time access to the 2 items right now.
Right, so what I'll do is I'll look at, say, the 2 items closest to the middle, and I'll notice that, in this case, it's decreasing. Okay, now if the profile that I see in my array is, well, it's increasing here and it's decreasing on the ends, which is exactly the opposite of what I just said, so no, that doesn't help. Sorry, let's try that again. Sometimes I could swear this is up. Okay, so it's increasing on the boundaries and it's decreasing in the middle. Where is the minimum element? It's got to be in the right half. Right? The local max has got to be on the left, and the local min has got to be on the right. Okay? So in this case, I would throw out the left half of the array and recurse on the right. Okay? Now, for something slightly harder, what if I see this? 1 is bigger than an, and n over 2 is bigger than n over 2 minus 1. Yep.
Couldn't it also decrease in the middle of
Here? Or what do you mean?
the second one, like
Yeah.
in the middle somewhere in each half to go down?
Right, so based on the information I have so far, I don't actually know whether this profile looks like this or like this. Right? I don't know whether the minimum is on the left or on the right, but you're very close to being able to tell. Yeah.
How do you not know if
You've looked at 4 elements out of a 1 billion element array. You have not seen the smallest element yet.
Yeah, but I'm saying you know it's going to,
Why do you know it's going to be on the right?
because the left is,
Okay, let me give you 2 examples. 5, 4, 10, 12. In this case, I could fill in, 2 more numbers. And notice the median is on the right. 5, 4, 1, 2, 0, 3. In this case, the median, the minimum element is on the left. But in both of these cases, you see up on the ends and up in the middle. In one, the minimum is on the left, and the other one, the minimum is on the right. How do I distinguish between those 2 cases? Say that again, but without pronouns. What is an array that's always increasing? No, you've looked at 4 elements. These 2 are in this order, and these 2 are in this order. That's all you've done, 2 comparisons. That's all the arrows represent. So how do I tell these 2 cases apart? Yeah.
If the value in the middle is higher than the value of
Yes. So I'm going to do one more comparison. Right? So here I've compared between the 2 orange things already, and now I've compared between these 2 pink things already. And in the second case, I'm going to do one more comparison between these 2 pairs. Okay? So notice here, right? So if A1 is greater than AN, then there'll be an else case. If A sub M is greater than A sub M minus M plus 1, then recurse on the right. Otherwise, I'll compare A1 to AM. If A1 is smaller than AM, but notice, I'm increasing at the beginning, and I'm increasing in the middle, but I'm higher up. The only way that could possibly happen is if the minimum is on the right? Because if the minimum is on the left, then I have to keep increasing. After I leave the minimum, I have to go up, 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 up from 10, and then I get, wait, that's too low. I got the contradiction. Okay. So in this case, the entire left side of the array, this is the case at the top, the entire left side of the array must be increasing. And so, again, I'll recurse on the right, else I recurse on the left. Yeah?
So just make sure I'm understanding this right. You're saying if the
Right. If I'm increasing at the boundary, and I'm increasing at the middle, and the middle is higher than the boundary, then the entire left side of the array must be increasing, and which means the local minimum must be on the right. Okay. And then there's clearly 3 more cases that happen if A1 is less than AN. They're just symmetric. Yeah.
You want to compare the endpoint?
First line, if A1 is bigger than AN, so maybe I don't understand the question. The algorithm that I'm proposing does compare the endpoints. So maybe I don't understand what you mean by do you have to?
So the minimum must occur.
I'm sorry?
The minimum, the smallest element in the array must occur at the
The minimum element in the array can be anywhere whatsoever in the array. But it must be the only element in the array that's smaller than its 2 neighbors. That's what it means for the array to be bitonic. Right? So I do have to be a little bit careful here. There's some possibilities just as a sanity check. What happens if the minimum element is right at A1? What happens if the minimum element is right at AN? what happens if the minimum element is right in the middle, right? So if I want to be a little bit safe, when I recurse on a window that is bigger by a couple of elements, and then I let the base case be, when I have less than 20 elements, just use brute force. But the basic idea, aside from the sort of boundary issues, is with a constant number of comparisons, I get to throw away half the array, which is exactly binary search. Yeah.
So you defined by like
Yeah.
in the case where you recurse to the right, how do you make sure that
Well, okay, suppose I'm in the case where I want to recurse to the right. How do I know that there's no local minimum on the left, right? So suppose there is a local minimum on the left. Well, I'm increasing here, and well, I have to go to the local minimum, and then I'm increasing again. Okay, I had to have, if I had a local min on the left, I also had to have the local max on the left, right? But now there's no room for a local max here, even though in the end I have to go down. Right? So the only way to get, I have to go down again, and now I've contradicted the definition of bitonic. Now the interesting thing is, suppose I give you an array that has two local maxes and two local mins. Right, so the array looks like this. There is no way to find the minimum with less than n comparisons. You have to look at every single element in the array in that case. And the proof is, I'm going to give you an array that goes from 1 to n, except somewhere in the middle I'm going to jump down to minus infinity. I'm not going to tell you where. But when you ask me about the array, anytime you ask me, hey, what's in this slot? If you ask me what's in slot I, I'm going to tell you I. I'm just going to lie to you. And so if you end up looking at every element in the array, you've used linear time and I'm happy, and then, okay, A1 is the right answer. But if there's some spot in the array that you don't look at, I'm going to surreptitiously change that to a minus infinity, but you can't tell because you never asked about that. And so the one thing you didn't ask about will be the right answer. Right? This is called an adversary argument. So there's really something very special about only having one local max. Notice that there are two local maxes in this array. Having only one local max that allows you to find things faster. Once you have two, all bets are off. All right. Tangent. Any other questions about? Yeah. Okay, could you read it? What's the problem? Okay, so this is the class scheduling problem. Sorry, if x and y are disjoint, choose x. Okay. Discard x. Okay. Okay, so if you've gone through the list of strategies in that question, by process of elimination, hopefully you've discovered that counterexamples for all but 3 of them, and the question says 3 of these strategies actually work. This is one that the claim is that it actually does work. Okay? So let me go through this one step at a time. There are basically 3 things to prove. Okay? One is that if these first 2 classes, the first and second starting classes, are disjoint, then there is an optimal schedule that contains X. The second is if the first 2 classes are nested, then there is an optimal schedule that does not include X. And in the last case, if they overlap but they're not nested, there is an optimal schedule that does not contain Y. Okay? So let me look at these one at a time. Okay? Here's X, here's Y, and everything else starts after Y. Okay? Now, suppose I have a schedule that does not include X. Okay, for the sake of argument. Then, because X ends before any other class begins, I can just add X to that schedule and get something better. Okay? So, if X and Y are disjoint, then in fact every optimal schedule contains X, which is equivalent to saying any schedule that doesn't contain X can't be optimal, because then I could add X to it. Okay? So that's the first thing I need to prove. Okay, so the second one, case 2, is here's X and here's Y, and everything else starts after Y starts. Okay? And what I want to show is that there is an optimal schedule that does not contain X. Okay, so for the sake of argument, suppose I have a schedule that contains X. That schedule cannot contain anything that overlaps with X, and therefore that schedule cannot contain anything that overlaps with Y. So if I exchange X for Y, if I throw out, so instead of including X, I throw out X and include Y, I still have a valid schedule. So I haven't made things, by exchanging X and Y, I haven't made things worse. So then that's the end of the proof. Okay. If Y is contained in X, then some optimal schedule excludes X. Okay. The third possibility is that they're not disjoint and they're not nested, and in this case, that means that X and Y must be related like this. X starts before Y, but X must also end before Y. Okay? And now, again, and everything else starts after Y starts. So, maybe the rest of the schedule looks like, the rest of the classes look like this. All right? And now what I want to show is that there is an optimal schedule that excludes Y. All right? So suppose I have a schedule that includes Y. Well, then that schedule must exclude every class that conflicts with Y. But that means that it must also exclude every class that conflicts with X. Right? Now, in principle, there might be classes that conflict with X but not Y, but those don't exist because nothing starts between the beginning of X and the beginning of Y. There are no classes that conflict with just this little window. Anything that touches X also touches Y. Okay? So again, I can throw out Y and include X instead, and I still have a valid schedule. Okay? So if X and Y intersect but are not nested, some optimal schedule excludes Y. Okay, and so what the greedy algorithm is doing is saying, well, there are three possibilities for how the first two classes can intersect. And in each one of those three cases, I can argue that either X has to be included, X can be thrown out, or Y can be thrown out. And so I just do that, and I recurse on everything that's left. Yeah.
X and Y started at the same time.
Then X and Y are nested.
But there were no classes that started until Y was done. Which one was the greedy algorithm?
So you're interested in, okay, so here is X, and Y is twice as long.
Or just longer.
Okay, Y is longer. And then there's other stuff.
Well, no, there's no classes until Y ends.
Until Y ends.
Yeah.
So there's a window here and, okay. So let's look at the algorithm. X and Y are disjoint? No. Is Y contained in X? No. So I discard Y. The algorithm throws out Y and recurses.
Why does it?
Why should it? Because it doesn't, because that's not the code that was written down. It does because it doesn't have to. Right? Remember, the goal is just to choose the maximum number of classes. I'm not trying to maximize the amount of time that I'm in class. Yes?
So to the extent we have to elaborate.
So on an exam, I would not ask you anything that requires, these three separate arguments. It would be, something that would require one of those arguments. And then, yes, I would want you to actually say what I said out loud on paper. Suppose there's a schedule that contains Y, then it must exclude anything that conflicts with Y, and therefore it must exclude everything that conflicts with X. And so deleting Y and inserting X leaves you with a valid schedule. Therefore, right, just write the three, 4 sentences to fill in the details. Yeah.
I think this is a homework problem, but
Okay, that was a homework problem. I'll answer it as soon as everybody says they're okay with the greedy thing, because it's a different problem. Everybody cool with, all right, good. So, here I want to schedule non-overlapping classes to maximize the total credit hours. Okay. So, it's in the neighborhood of something that we solved with the greedy algorithm, and therefore I can conclude immediately that we should use dynamic programming. I'm really completely serious about this. If you ever notice that you have written down the word greedy, that means the correct answer is dynamic programming. Okay, so this looks like some sort of dynamic programming thing, so I'm going to try to follow this general strategy of answering dynamic programming questions. Which is first, let me develop some kind of recursive backtracking algorithm. So each of these classes has some number of credit hours attached to it. Okay. And the question that I'm going to start with is, hey, there's this class that I picked first in the greedy algorithm. Let's go ahead and sort the classes by their finishing times, because that seemed to be useful before. So sort by finish. All right, so I'm going to consider impose some ordering on the classes. And then I'll look at the first class that's available and ask, should I take this class or not? If a birdie landed on my shoulder and says, don't take that class, then it's clear what to do. I just throw that class away and I recurse on everything else. Okay. If, on the other hand, I decide I do want to take this class, now I want to recurse on other things, but it's not quite as straightforward as just recursively compute a schedule for everything else, because that throws away information about the decisions I've already made. Somehow I need to remember that I've signed up for a class that ends here, and that therefore I should only register for classes that end after that finishing time, out of the remaining classes that I haven't thought about yet. Okay, so now when I'm recursing, I'm actually carrying around two pieces of information. One, when was the last class I signed up for? When does that end? And two, how many classes do I have left to think about? So I'm going to end up with a two-parameter recurrence. Okay? So let me show you one way that I could define that recurrence. So maximum hours ij, this is the maximum number of hours that I can get from classes j through n. So class j is the first one I'm allowed to think about, but that all end after class I, or sorry, that all begin after class I ends. And then if I want to solve the original problem, maybe I can set up a fictional class 0 that ends at the beginning of time, and then when I call the function, I'll call max hours of 0, 1. Okay. All right. So now, again, I need to set up a recurrence for this. The base case is going to be there are no classes left to think about. So if j is bigger than n, that means I've already recursed my way down to the empty set of classes. How many hours can I get by not taking any classes? 0. Good. Otherwise, I need to look at class j and decide whether or not to take it. Now, it may be that I have the freedom to take class j, and it may be that I'm forced not to take class j. So in particular, if class j starts before class I finishes, then I can't take class j. There's no decision to be made, And so I should recurse by keeping the same, the class I registered for last stays the same, but now I'm considering classes starting at index j plus 1 as things I haven't thought about yet. Otherwise, there are two possibilities, and I want the larger of them. One is that I don't take class J. We've already seen what that expression looks like. The other is I do take class J. And if I do take class J, then I add some number of hours to my schedule, and then I recurse, but remembering that the most recent class I signed up for was class J, and then I need to think about the remaining classes starting at j plus 1. Okay? So I have this two-parameter recurrence, where the first parameter tells me this is the time that the last class gets out, so that I've registered for so far, and the other parameter says this is the first class that I haven't thought about yet, haven't made a decision about. Now I literally put aside the definition of this and just look at this as a recurrence without thinking about what it means. How would I memorize this? I need a 2D array indexed by I and j. It just so happens that I is always going to be less than j, but whatever, right? And then if I want to fill in the box at a particular row and column I and j, what other values do I need to fill in before that? No, look at the recurrence. Don't think about what a recurrence means. Look at the actual code on the page. If I want to evaluate this, what other things do I have to evaluate? Right, ij plus 1, so same row, one later column, and jj plus 1, which is just above the main diagonal. So before I fill in the white box, I have to have already filled in the black boxes. So what order should I evaluate the array? So right to left, and if I do that in the outer loop, it actually doesn't matter whether the inner loop is up or down, because there's no dependencies in the same column. Okay, and then how long does it take to do this? We're done. Okay. This, by the way, English, recurrence, cartoon, running time. I guess the one last thing you need is we want max hours of 0, 1, where f of 0 is minus infinity. Okay, you need to say how to invoke the function at the beginning. This is full credit. Yeah.
Do we need the for loops that accompany the cartoon?
No. The arrows tell you what the for loops would look like. If it is more convenient, more intuitive for you to write out the iterative pseudocode instead of writing out the recurrence and the cartoon, write down the iterative pseudocode instead of writing down the recurrence and the cartoon. But even if you do that, please remember to tell me what the function you're evaluating means in English. All right. Yes?
I'm trying to see it, but why is it that
Because the white box does not depend on anything above it, and it does not depend on anything below it in the same column. no, it's to the right. Remember, the outer loop is more significant. So the fact that it's to the right matters more than the fact that it's below.
So this loop would be outer.
Yeah, the double arrow, I mean, the standard that I use is the double arrow means the outer loop, and the single arrow means the inner loop. Now, I could swap and do row by row, a vertical arrow in the outer loop, and then you would be right. I would have to go up in the outer loop, and I would still have to go right to left in the inner loop. Right? So this order also works. And this order also works. But this order does not work. Because what would happen is, as I'm evaluating, I would get to row I. Oh no, that order actually does work. What am I saying? I go down. Oh no, this order doesn't work. Because when I get to row I haven't evaluated this thing down here at the diagonal yet. Right. Yes. Right, so when you write out, if you wanted to implement this dynamic programming algorithm in code, you would have to fill in this array for all values of I and j. So you're going to have two for loops. For I equals something for I equals 1 to n, either in increasing or decreasing order, and for j equals 1 to n in either decreasing or increasing order. And you have a choice about whether you have I as the outer loop or j as the outer loop. What this arrows mean is the outer loop is for j equals n down to 0. The double arrow means it's the outer loop. And the inner loop, the single arrow, means it's for I equals 1 to n. So whether it's double or single tells you whether it's inside or out, and then the direction of the arrow tells you whether you want a loop going up or loop going down. Yeah?
If we mess up the evaluation order and our memorization, how does that affect our?
So up to this point is 6 points out of 10. And then it's basically 1 point for telling me the data structure, 2 points for telling me the evaluation order, 1 point for telling me the running time.
So incorrect.
Incorrect evaluation order, you'd lose 2 points. I think that's what the rubric says in the dynamic programming homework. If everything is correct, but you write n here, you get 9 points. If what you actually describe is an algorithm that runs in n cubed time, and you write n squared here, you don't get credit for the running time because you're supposed to tell me the running time of your algorithm, not the running time of my algorithm that you don't know. And you would lose points because your algorithm is slower than the target we're expecting. Right? So having an n cubed algorithm and saying it runs an n squared might be worth only 6 points, even though the correct algorithm runs at n squared time. Right. As long as everything is correct, you just keep accumulating points. At the end, if it turns out your algorithm is slower than the one we're expecting, we'll scale. Right? The more difficult question is, if you get this wrong, then you're screwed from the beginning. If you can't tell us what you're doing, then there's no way, even in principle, to tell whether you're doing it right. Right? And then if you get this right, but you screw up the recursive cases, then it doesn't matter how you implement it, you're going to get the wrong answer. Right? But if you get the recurrence right, okay, good, then maybe you get the evaluation order wrong, then you're getting closer to a correct answer, and so you could get more points. Yeah. Well, then you'd stop here. Yeah. Right.
Can I get more points if
Ah, the $64,000 question. There's always this fight between I know a little bit, but I know I don't know the whole answer. Should I write down what I know, or should I say I don't know? And where I would actually draw that line is if you can get past here, write down what you know. But up to this point, you're looking at maybe 3 points out of 10 at most. Just over the I don't know line, and even this much, it's, if you can only get this far, there's a fair chance that the function you chose to memorize isn't going to work out. Yeah. So the rule about I don't know is you can do two things. One, you can write down an answer, and we'll give you a grade. Two, you can write down I don't know, and we'll give you 2.5 points. Not, you write down half of an answer and I don't know the rest. Right? There's actually some discussion about whether this is the right thing to do, but for now, the course policy is you can just decide big X, I don't know, or you can write something down and submit it for a grade. Right? Generally speaking, if we notice that you have crossed out something worth 6 points and written I don't know under it, you'll get the 6 points anyway. Right? So I do recommend using X's instead of a big fat eraser, right? Don't, scribble it out in disgust to the point where we can't read it. If you're almost right, we would prefer to actually give you credit because it reflects your actual ability rather than having you suffer for a lack of confidence. Right? Your grade is supposed to reflect how well you know the material, not how well you think you know the material in either direction. Right? So, try everything. Try doing everything. Don't just sort of go, bah, I don't know. Right? But after you try, then at the end when I say, okay, everybody, turn in your exams, you have the option of going, I don't know. Now, I really mean if it's significantly more than I don't know. Right? If it looks like, hey, this looks like a perfectly reasonable recurrence. Why did you cross that out? I'll just erase the I don't know. Okay. Yeah? Okay, can you tell me the problem? So directed acyclic graph, unique source, S, unique sink, T. Okay? Find the maximum weight path from S to T. Okay, so when you see the words directed acyclic graph, what does your hand immediately write without you even thinking about it on the exam? Good. So I go, directed acyclic graph, okay, good. Topological sort, G. All right, now let me read the rest of the problem. Okay. This is like prove prove that for all positive integers, let n be an arbitrary positive integer, that blah, blah, blah. Okay, right. Don't wait to read the rest of the problem before you start writing things down. Yeah?
I think I understand topological sort.
Okay, so the goal of topological sort is to assign an index, a number, to every vertex so that every edge goes from a lower numbered vertex to a higher numbered vertex. Okay, you want to sort the vertices so that all the edges go in one direction.
So the way I always thought about it was that
It's a little bit fuzzy. So if you're thinking about a DAG as like a dependency graph in your source control system, whatever, the topological sorting tells you the order you should compile. You should compile earlier things in the compilation chain before later things. But if they're independent, if there are two files that don't depend on each other, it doesn't matter which order. Yeah?
What are the numbers for topological sort actually represent in form of graph?
Order. All it represents is order. This vertex should come before that one, should come before this other one.
Some ordering?
Some order that obeys this constraint. So you can think of it as, I'm going to build an array. Every element in this array is going to point to a vertex. And every edge in the graph, after I've done this assignment, is going to point from a lower numbered thing to a higher numbered thing. Once I've done that, I can now think about paths in the graph as subsequences of this array. And we know how to do subsequence things. Yeah.
I was going to say, I assume you don't get that for free. That looks like.
Yeah. This takes order v plus e time.
Okay.
Right. But pretty much, you can be fairly sure that anything else you do from now on is also going to take at least that much time. And so in the end, it all washes out. Okay, so I remember paths and DAGs are subsequences of vertices in this order. So I'm going to do what I normally do with a subsequence, which is develop a dynamic programming algorithm. And that starts by developing a recurrence. So one way to do this is the following. So the question that I might ask when I'm thinking about a path is this the first edge? Where do I know I'm going to start at S. Where am I going to go to next? I know I'm going to end at T. Where did I come from last? So in this case, I'm going to imagine that the question I ask is, what is the last edge on the path? And if a little birdie lands on my shoulder and says, the last edge is this one, it goes from V to T, then the next question I have to ask, or rather that I have to ask the recursion fairy to answer, is how do I get from S to V? And then a little birdie lands on my shoulder and says, you go from U to V last. And then I have to ask about from S to U. The source of my path is never changing, but the destination of my path is changing. So that's going to be the parameter for my recurrence. Okay. So I need some base cases. Anyone? So if S equals V, then any path is going to contain S. The total weight of the path is just the weight of that vertex S. Okay? Any other base cases you want to think about? Well, V equals T isn't going to be a base case. V equals T is going to be the way we call the function at the top. Yeah. There's only one sink. There's only one source. T is a sink. It's the only sink. Therefore, it's here. The last vertex in topological order is always a sink, because all the edges that touch it come from the left and go in. All right? So T has to end up here, S has to end up here. For more general DAGs, you'd be right. Thinking about a DAG that has more sources and sinks, generally you might have to do something special at sources. You might have to do something special at sinks. But because I said unique source and sink, that there are no other cases other than S and T. And we know how to deal with S, and T isn't anything special. That's how we're going to call the function at the beginning. So what do we do in the middle? Okay, so presumably I want to maximize something over all edges leaving V. No, yeah, the question I want to ask is what's the last edge? So actually I want to maximize from U into V. And then, given that I've decided on a particular U, what is the length of the path going to be? So remember the vertices have weights in this case. So I'm always going to use the weight of V. Always. And then the rest of the path, the only question I have to ask is where does the rest of the path end? If it ends at U, then I want the best way to get to U. Okay? How do I memorize this recurrence? 1D array. Or, equivalently, I store this value at V. Right? Let's imagine that I memorize it into an array. What's the evaluation order? If I want to fill in this spot for V, what do I have to evaluate first? Some stuff to the left, because I don't necessarily know which things to the left. But, I mean, these are exactly going to correspond to the edges coming into V. So what order do I evaluate? Left to right. This is just a standard for I equals 1 to n. And then finally, what's the running time? So let's think about let's think about this carefully. Okay, time is going to be. We'll have to evaluate this quantity for every vertex V. And then how much time do I spend on vertex V? So, well, I spend constant time looking up W of V plus the number of vertices coming into, the number of edges coming into V. This sum is equal to V plus E. Every vertex is counted once, and every edge is counted once. Yes?
What does that notation mean?
This is the maximum over all choices of incoming edges of the recursive call max W of U. Yeah?
Just out of curiosity, why did we choose to build this?
Because I wanted to end up with an arrow that pointed to the right. Because this way I can say, for all vertices in topological order, do the following. If I did it the other way, I could say, for all vertices in reverse topological order, do the following. Actually, if you were implementing this, probably you'd want to do reverse topological order because that's the same as post order when you're doing a DFS. There was another question? Yeah?
Yeah, so conversely, you can evaluate the outgoing edges from U2, because
Well, at this point, I don't know what U is. The only argument to my function is V. U is a local variable that I have that's bound to this max. Okay. I guess I will see almost all of you in 5 hours. And then you will not see me again after 7 hours. Yeah.
Location of the conflict been determined yet?
No, not yet. Just